Kwek, will so that it's just 2 minutes left to 3 p.m. here. So in 2 minutes we'll actually start.
Sure.
Hello, hello.
Yeah. Should I start?
Yeah, hello.
Hi.
Uh, okay, so I think we are just going to start our uh, session. So to our speaker, I mean, let me introduce our center first. So Center for Quantum Engineering Research and Education is one of the centers of TCG Crest, Kolkata. The center is dedicated to work in the frontier areas of quantum science and technology. So work is going on in particular in the area of quantum computation theory and experiment, quantum metrology and sensing theory and experiment, and quantum communication and foundation. Now we also have an active PhD program. Now UN has declared 2025 as a international year for quantum science and technology. The center is celebrating this year with a series of colloquiums as well as 4 conferences. So we are very happy and privileged to have Professor Elsie Kwek from National University of Singapore, Center for Quantum Technology, National University of Singapore, as one of speakers in our series. And Professor Kwek is associated with the Center for Quantum Technology, National Institute of Singapore, and also Center for Engineering for Quantum Science and Technology, Nanyang University. Professor Kwek has, contributed very significantly to various areas of quantum science and technology. He has more than 300 publications in the leading journals like Nature Photonics, Nature Communication, Physical Review Letters, to name a few. He has also won many prestigious awards. Also, he is a member of many international societies. He is also served in many international organizations. And so we are actually very happy and privileged to have him as one of the speakers. Okay, so he is going to speak today on quantum and optical technology with integrated silicon photonics. Yeah, and title has changed a bit. So now I am welcoming Professor Kwek on behalf of the and requesting him to give his colloquium.
Thank you for Shiptas for the kind invitation as well as for the kind words. Today I'm going to talk about essentially it's integrated silicon photonics. for quantum or optical technologies or applications. So you can morph the title a little bit. It doesn't really matter. Now, I'm also very delighted, in fact, to see that your center is a center for quantum engineering and research, but more importantly, an education. And to me, I think one of the most important aspect of quantum science and technology is application, or rather is introduction to education. So how do we teach quantum science and how do we teach quantum technologies in the next few decades? This is a matter of deep importance in many ways. Okay, so let me start. So why integrated photonic circuits? Well, integrated electronics has been ongoing for a long time. We have seen that it has led to the current technology right now with computers and also with the radio system and also the television and all communication devices. Electrons, of course, are very small, but we need to bear in mind that so are photons. In fact, photons are massless and they move really, really fast. Nothing faster than photons. And it's not just the speed of light that is exciting. It is also the capacity of optical fiber. Electrons moving through a copper wire carry a limited amount of data and over short distances with a lot of heat and energy loss. We see that in our current push towards machine learning. There's a lot of heat and energy loss that's needed for the training purposes. Optics, on the other hand, of course, is capable of carrying multiple signals within a single waveguide. And this capability is known as multiplexing in some sense. The high frequency range of electromagnetic field also increase the bandwidth and also the speed of the circuit without significantly generating heat. So these are some pros and cons. But can photons do better than electrons? Now, we have already known way back from Schrödinger that matters can interact and form non-classical correlation. And these non-classical correlations can be formed with photons in the sense that if one side register a coin toss 1, then the other side will also simultaneously register 1, or could be 0, but perfectly correlated or anti-correlated. So basically, if one side get 1, 0, 1, 1, so does the other. The other side will get 1, 0, 1, 1. This is correlated rubbish, or sometimes called spooky action at a distance, but nevertheless, it is correlated rubbish. At the end of the day, it doesn't convey any information. But this is precisely the thing that in cryptography, many people wanted. That is correlated rubbish. I will come back to that later. So we note that there is no real information transmitted between the two parties, typically called Alice and Bob. And in fact, this correlation go as far, the experimental proof go as far back as the 1949, when C.S. Wool and Ivan Shaknov shown that you can get coincidence measurements that are above the classical rate in some sense. So in this case, they prove that you can get quantum correlation. So this is probably one of the first paper to show entangled pairs in a lot of sense. In 1967, Kosher and Cummins also did another experiment, and showed something akin to what's now called Bell inequality. But except that they had a fixed setting, so this was not randomized, and was on an atomic scale. These were early experiments, but the pinning experiment probably came from uh, uh, firstly by Freeman and then by our good friend Freeman and Clauser, and also by our good friend from France, Philippe Granger, Gerard Roger, and Alan Aspect. In particular, Alan Aspect lead the experiment to show that you can actually violate Bell inequalities, which is a set of inequalities that all classical correlation must obey, uh, in some sense. But if you have a quantum object that is distributed between the two parties, then this inequality, that S in this particular case need to lie between -2 and 2, will be violated for quantum objects. This was made to longer and longer distance by Gison's group in Geneva, to more than 10 kilometers, and people could still prove it. And then also at the same time by Anton Zellinger, to a large extent, over in Austria. And there were also other experiments with Bell inequality, with efficient detections done in the United States. Not go in deep details. And this one was with trapped ions, where they proved that one could violate Bell inequality. And this is another experiment from the Jason group, where they showed that space-like separation in a Bell test of several kilometers apart between 3 cities. Violation is also found in solid-state devices, Josephson junctions, and proposed, in fact, by Anton himself for huge distances in outer space, a cosmic Bell test. Cosmic Bell test with quasar was also suggested. Experimentally, satellite-based entanglement distribution over 1,200 kilometers have been shown by the Chinese team, led by Jian Weipan. And this was over 3 cities, actually, Urumqi, Nagari, and Lijiang in China, Delinga, actually, 4 cities. And they were able to communicate with Europe to some extent in this other paper. And existing collaborations with Italy, Germany, Russia, Singapore, and Sweden are ongoing. Loophole Bell test violation separated by 1.3 kilometers can also be done. So far, we have been talking about photons, but it can also be done with electrons and also atoms. And so this was a paper that showed that electrons also. But at the end of the day, we need to note that electrons are much harder because they interact with the channels, and so they are not exactly as efficient in inverted comma as photons. So these are experiments with electrons and also with atoms. In both cases, electrons and atoms, they interact with the medium. So we expect a lot of problems, challenges. So a little brief history, very brief, on integrated photonic chip and why silicon. Silicon is very cheap. In some sense, it's the sand that lies on our beaches. And so it'll be interesting why if quantum experiment can be done on silicon platform, just very much like the electronics industry, which is very much based on silicon. So there's a roadmap for integrated photonics for quantum devices, and there are some key features. The improvement in transparency, in material, in stability, in power have been shown over the years from 2016 all the way to 2035. Technology for silicon was introduced in the 70s or even late 60s. But I think it's but they're mainly restricted to electrons. So what we are more concerned with is the proof of at least the ability for photons to be scaled down on silicon chips. So the first scaled down version on chip quantum interference experiment at CNOT was actually performed way back in 2008 or 9 by the Bristol group. And then it has since progressed very much. We'll go into that history. The first experiment was a very simple one in which they showed that with two wires coming together, it forms a beam splitter. So light that comes in here after evanescent coupling could either go forward in this path or to the other path. So this is essentially a beam splitter. And then they construct an asymmetric beam splitter together with some phase shifters to form what is called the C-phase gate or the C-naught gate eventually. Okay. And this was proven to be possible by, of course, photonics being photonics. This device is actually not deterministic like our current superconducting qubit or ion trap. This was actually probabilistic, which means that there is some high probability that it fails. And if you concatenate further, this probability goes down. So that was the initial stage. And then there were lots of some proof of principle experiment, including Shaw algorithm being shown on this chip-based type of silicon technology. But as you can see, it is involve a input state that is at most 8, 0 to 8, or 7 for that matter. But what was interesting was that they were showing various things. And one of them was the fact that you can actually laser write these fibers on silicon chip. Now, the technique of laser writing was very slow at first, but nowadays you can do it very fast. But the advantage of this was that was a technique that could overcome a problem, an engineering problem, essentially, on polarization. It was found out that if you have a beam splitter, horizontal polarization do not have the same ratio as vertical polarization. So in order to get them to be a 50-50 for both horizontal and vertical polarization, it was necessary, in fact, to tilt this plane where the beam splitter lies. And by tilting the plane, you find that while one of the polarization degree of freedom goes up, the other goes down. So there's a sweet spot somewhere in between, some angles, such that you get a 50-50 beam splitter for both horizontal and vertical polarization. And so this technique was fully exploited in what's called quantum walk. So lots of quantum walk experiments were then performed ingeniously. Now, the next idea, of course, is we start off with Bell inequality. In fact, one of the most important application of Bell inequality is quantum key distribution. That is to distribute two rubbish key between two parties. I reiterate, is two rubbish key or two rubbish information between two parties. And in fact, in Singapore, our foray into this into this technology starts with quantum key distribution at the beginning. So that was way back in roughly 2019 or 18, just before the COVID period, when we decided that, maybe we can put the quantum key distribution onto a tiny chip, silicon chip. And we start off with continuous variable protocol. We're using a coherent beam. So one of the important things why we were more interested in continuous key distribution at that time was that it has the advantage that it is fully compatible with the existing optical platform. So we don't need dark fibers. We just use the existing optical network, which is readily available, and then we just conduct the test. And why do we want to do this? It's basically to scale down the component. Essentially, this was the first experiments on key distribution, and we hope that it will be scaled down several millions of orders into a tiny chip. And ultimately, we hope that this chip will be embedded inside the handphone. At that time, this was a novel idea, and I think some companies were interested in it, except that we didn't fully exploit it. Some companies have actually gone on to manufacture telephones or mobiles that incorporate such chips. And the idea was that for us, it was that we could then popularize quantum key distribution among not scientists, but just young kids. Because by popularizing a technology, I don't know what young kids want to do with cryptography, but nevertheless, they can share secrets among themselves, away from their girlfriends or away from their boyfriends, and certainly this is something to play around with. And so we wanted to put it onto the handphone for them to play as a game. And hopefully, after all, hopefully they will get used to it. And after all, within the mobile phone, we have plenty. In fact, this mobile phone, yeah, we have plenty of useless applications. So why not one more? And so we also tried to do this. We showed that was possible. And later on, during just before the COVID and period, we embarked on trying to put MDI QKD. If you know what that means, is measurement device independent quantum key distribution onto a chip as well. But in this case, of course, we need three parties: Alice, Bob, and Charlie. And Alice and Bob send the information to Charlie. Charlie does some measurement and publicly announce it. And as a result, Alice and Bob get their rubbish key. Essentially, the idea in this MDI QKD is entanglement swapping. Alice and Charlie get entangled. Bob and Charlie get entangled. But when Charlie measures his 2 qubits, Alice and Bob, he destroys the entanglement in his side, but Alice and Bob then automatically get entangled. So that's the key idea behind MDI QKD. The next thing we tried to use this optical chip for was to say, that we can actually manufacture any unitary gates with these silicon chips. So, and we can control them using phase shifter, but this is very much similar to neural network machine learning, where in neural network, of course, you adjust the weights. And in our case, we adjust the phases. So a little bit, let's switch gear a moment to go into some why I was interested in neural network. I did some experiments with rats in the earlier days, somewhat like 25 years ago. where we put optical fiber and we just insert it in through the anus into the intestine. And then this is at that time it was very, very coarse optical fiber. And so sometimes, but even then it was very sharp, and sometimes they poke through the intestine and then the rat dies. So this is the tumor cells that's from the rats. And these are the tumors that's induced in some of the rats. On the confocal microscope, you can see the difference between normal tissue and tumor tissues. And then what we did was that we do what's called laser-induced autofluorescence. We shine light in, and we collect the reflected light. Everything is fine. You get a spectrum depending on the wavelength that you inject, and then you see the intensity. The intensity for tumor cells, they tend to have certain peaks that are non-existent for normal cells. So we took the ratio, and it was a good indicator. Not very good for medical terms, but certainly good for us. It's around 80% accuracy. And then we decided at some stage to use the result that we have with what's called neural network. At that time, this was way back in 2005 or even before. Machine learning is not in vogue. In fact, many people view a neural network very skeptically, unlike the current situation. And at that time, we could show that with neural network, we could classify accuracy, sensitivity of 99.2 and a specificity of 99.4. So it was very nice because we could use perceptron type of ANN, artificial neural network to classify between tumor cells and non-tumor cells. So in the next part, way back in around 2020, we decided that we should use the same optical chip and implement so-called complex value neural network. After all, our phase are complex numbers. So we are actually changing weights, of course, but the weights are complex value. And complex value, and in fact, has only recently begun in computer science literature. And this was a chip that we made. This is the interferometer. And we could show that you could implement an artificial neural network for classification of various things, iris data, MDs, with a very simple chip. And you see here that this is the chip, the structure, the inside structure. Each one of these, beam splitter, phase shifter, probably another phase shifter here, forms what's called SU2 gates. In some sense, it's unitary gates, but only for that particular line. And if you concatenate them in such a structure, you can prove that if you have a single photon coming in, then depending on where the single photon goes, it tells you what this unitary gate is. So in fact, we can use single photon to characterize this gate, and then use this gate to represent that arbitrary unitary. Well, depending on what unitary you want to do. And since we use a unitary, this is no longer well, in some sense, no longer a classical neural network. It is really embedded within it is an optical chip, or some sense it uses interference. And so we call it at that time quantum neural network to a large extent. But nowadays, of course, I do not want to go into the debate whether this is quantum or classical. Certainly, it implements a unitary gate at a photonic level, and it could, more importantly, classify various data sets. And we find that we could also classify data sets for computational chemistry. Depending on the different types of molecules, we could predict the enthalpy or entropy. Everything regressional analysis with a very good testing score of 93%. And then we compactify the chip further. At the beginning, it was 1 centimeter by half a centimeter. Then we compactify it to less than a centimeter by a few millimeter. So this was done with efficient use of space with a diffractive neural network. And we use some of these applications, this chip design, to do financial applications by this proof of principle, of course. So that was how the experiment goes. On this tiny chip, you have a Monte Carlo circuit, but more importantly, this is a circuit that's used. The circuit is made up of several components. So this is 1 mm. This is pretty large. It's roughly about 2 mm, 1 centimeter, in fact. So this is 1 mm. So this is roughly 2 mm. And what is perhaps important is that we use also amplitude amplification in this protocol. And it's because of the amplitude amplification in the search algorithm. So first we let the stock price goes through and Monte Carlo, and then we decide on the best path by using amplitude amplification. So that's the whole situation. The first part represents the distribution of loading. The second part is the payoff function. The third part was a quantum amplitude estimation protocol. And it's this part where then we use single photon detectors to find the pricing. Also, we use what's called a unary approach, meaning that the first mode here may represent 0, 0, 1. Then the next one is 0, 0, 1, 0. And so we don't save very much in terms of Hilbert space, but nevertheless, it's a proof of principle and it seems to work. So this is what we did. We showed that. But more importantly, the same circuit can be used for what's called boson sampling. So I'll give you a brief rundown on boson sampling. Suppose you have 3 photons that's coming into a unitary circuit. So T is unitary. And you would like to find what's the probability of detecting a photon at the third, the fifth, the third, the fifth, and the sixth photon output modes. Now, this probability can actually be calculated. So your input state is A1, A2, A3, 3 photons acting on the vacuum. So that's how we represent it. And A1 can be written as, in terms of the matrix T, T11, B1, T12, B2, and so forth. A2 can be written as T21 and so forth. And A3 is T31. And if you expand this circuit, this expansion, you find that you can pick out terms in which you have 3, 5, and 6. So 3, then pick up the 5 and pick up the 6. So T13, T25, T36. So T13, T25, and T36. And this is one of the terms. In fact, the square of that becomes the probability. But in addition, you have to add other terms. The other terms would be, you could also have the fifth one, in the first one going to the fifth, the third one, and then the sixth one. And it turns out that if you look at the probability of this happening, it is really looking at the submatrix, T13, T15, T16, and you are actually looking somewhat like the determinant. The determinant is T13, T25 times T36. T13, T226 minus T13, T26, and T35. By the minus is precisely what gives the computational power. But for this particular case, you don't want a minus. In fact, the terms are T13, T25, T36 plus T13, T26, T35. So there are no minuses. And the fact that there are no minuses makes the computation very hard. And we call this not determinant, but permanence. And it turns out that the permanence will then, when you square the permanence, that will give you the probability of finding the of finding a photon in the third mode, the fifth mode, and the sixth mode. And this turns out to be very difficult if the matrix become larger and larger. Now this is if you read this review introduction, you will see more about permanence, and it has to do with distinguishability of paths. So I'll not go into that in detail, but way back in 2013, when the laser written chips were first formulated, there were many groups who were interested in showing boson sampling. And the reason for boson sampling to be shown was because of this computational advantage when U is large and the number of photons is large. So one of the first to do was by Andrew White in Australia, 2013. And at the same time, there were a couple of other groups. The Oxford group, led by Ian Walmsley, who is now at Imperial College, also did another experiment with 3 photons and about 5 modes or so. And also the group of Paolo Mataloni and Fabio Chiarino, where they showed this hexagonal configuration, this scheme of doing this triangular configuration. First proposed by Anton Zellinger's group and published in Nature. And the last one was by Philip Walter. So altogether, there were 4 experiments using very simple chip design, and they could show that one in principle can do boson sampling. Now, what about boson sampling in more detail? Suppose I have another unitary given by this, and this is the unitary gate. And there's one photon going in the first mode, another photon in the second mode. Then you would ask, instead of asking, in the previous case, it was 3, 5, and 6. Now, let's say we want all possible configuration. Well, you can just simply expand. You can do that with any software that you have. They will give you, or even by hand, they will give you all these probabilities. The probability of the output appearing 1 is 49. You can compute that probability. 020 is 8 out of 81, and so forth, and total probability. So this constitutes all the possible outputs that can be. And you can plot this. So the red one represents where the 2 photons, no 2 photons comes out through the same output port. Whereas the black one represents where the 2 photons are in output port 2 or 3. Notice there's no possibility of 2 output photons from the first mode. But in any case, you can plot a histogram like this. And then for you can also do boson sampling and consider theoretically with lost photon. And at the end of the day, you can plot a chart. This is really the histogram now, but with 16 modes and 3 photons. So these are 3 photons. The first one, way back here, is a photon in the first mode, the second mode, and the third mode, and nothing in the rest. Then 1, 2, and 4. So each one of these, the heights. And the top level represent the experiment. So they compare the green and the orangey lines to see how close they are. And you can see from this diagram, they are pretty good. With 4 photons, the number increases, the possible output combination increases to 1,820. In this particular plot, you are not allowing 2 or more photons in each mode. So you can see that you can simulate also this with 1 photon loss. And it's very much like a mirror image, right? So this is like mirror image, the real experiment together with the theory. But in order to go beyond a few photons, and you need to prove computational advantage, it was shown that, or argued that you need at least 30 photons. But 30 photons will be difficult, and so this prompt people to look into another direction, which is to use squeeze light. And squeeze light is first published in this paper by Christine Silverthorne group and Igor Shek, where they showed that you can use squeeze light to do boson sampling. The detailed study is in this longish paper. And the difference between boson sampling in its original form and Gaussian boson sampling is that instead of a single photon that's feed into the interferometer, now you feed squeeze light. No. And then you still look at the output configuration and classify all possible paths, which is, of course, proportional to the permanence of the submatrix. But with squeeze light, you have an infinitely many photons, right? Each one of these is not single photons. So basically, if you do the calculation, it is still proportional to the permanence, but it's proportional to what's called a Hafnian. And Hafnian is really a bigger matrix where you look at the permanence of 2 subblocks, on the off-diagonal elements. So Gaussian boson sampling was done again in China. The first experiment was by Jianwei Pan. And they showed that in principle, you could do it even with noise. Skip the details. You can see these beautiful reflection patterns, the experiment together with the theory. So they both agree. And a little bit about Hafnian, for those of you who are interested in the mathematics. Suppose you have a graph, 1, 2, 3, labeled 1, 2, 3, 4, 5, 6, 7, 8. So 8 vertices. And the vertices are all connected by these edges. Then you can simply write down the adjacency matrix, which is simply 1 is connected, the first row is connected to 2, to 5, to 4, 4 and 5. And then the second vertex is connected to 1, of course, and to 6, and to 7, and so forth. So you can write out the whole submatrix. It's called the adjacency matrix. If you write a simple program to find the Hafnian of this adjacency matrix, you actually find the total number of perfect graph matching, which is how many ways can you pair the vertices in such a way that they are connected by edges that exist in the graph. So this is one possible one. You connect 1 to 5. You pair 1 with 5, 2 to 6, 4 to 8, and 7 to 3. But you can also pair them differently. So 1, 5, 4, 8 is still there. 6, 7, and 2, 3. So you find a total number of possibilities. And in this particular case of a simple graph, there are 9 possibilities. And 9 happen to be the number corresponding to the Hafnian of this adjacency matrix. You can write a simple program and you show clearly that for this adjacency matrix, it is 9. And we showed that perfect graph matching can be done in a simple experiment. And this was shown later on that Gaussian boson sampling could solve very complicating graph problems in some sense. which is in some sense not surprising because we have shown that Hafnian was related to perfect graph matching. And also for some molecular docking problems. I'll skip this. More recently, we have tried to employ it, although it's the theory that lies behind this is well studied, in experimentally on a chip with for molecular vibronic spectra. And so the key idea is that it turns out that the probability of an electron transiting from one of the vibrational modes to another vibrational modes, so you want to find that, sometimes it's called the Frank-Condon factor, FCF, is actually proportional to the Hafnian of the submatrix, of some submatrix. And we showed that this is in fact possible, so we published it recently. For some simple molecules, and the simple molecules was formic acid, which is, as you know, a vital ingredient of how the ends communicate with each other. And we showed that the theory, this is the theory, we reverse the trend, and this is the experiment. They almost perfectly match. More complicated is thymine, one of the proteins that's essential for DNA. And we showed that in this particular case of thymine, the matching is also very good. But these are based on Frank-Condon factor, so we do. But there are other molecules that do not exactly have, just including a Frank-Condon factor wouldn't do. You have also to include the non-Frank-Condon factors. And these are the hexagonal, the simple hexagonal, 2 hexagon and 3 hexagonal. And we try to see if they match. And you can see that these already illustrate that non-Frank-Condon factors are present in these molecules. And what other things can we do with these Frank-Condon factors? Well, we can actually show that with and without excitation, so this is without excitation, the red one, and with excitation, the blue one, the spectrum differs. So that allows the chemists to learn something about excitation. So can we do better? We are hoping that at the moment, of course, in quantum computing, there are several very good platforms, superconducting qubit, the trapped ions, the quantum dots, for example, which the topological qubits was recently shown by Microsoft, the diamond vacancy, and we are hoping that we can contribute to a new platform called photonics. And because photonics is, photons are cheap, we hope that we could get a lot more in terms of lifetime and in terms of efficiency. And more recently, there is also the Michel Lukin's group in Harvard, where they showed that you can also do what's called neutral atoms quantum computing. So these are the quantum bits for the superconducting qubit. Let's look at them. The chip is also as tiny as ours, but the fridge is huge, right? And this is ion traps. The ion traps need temperature control, but the chip, of course, is small. So our purpose was, can we do something better by using these silicon chips, integrated photonic chips, to do computation? At the moment, we can safely say that to some extent, we can do it with cluster state, but scaling up is still a big problem for us. So we are hoping that one day we can do efficient photonic quantum computation with high-dimensional cluster state. And why do we want photonic quantum computation? It's because with photons, you just operate at room temperature. There's no need for the fridge. Things can get smaller. And not just that, things can also get more energy efficient. But the stumbling block, of course, is a paper by Keneal, Laflamme, and Milburn way back in 2000, where they showed that photonic quantum computers are not deterministic. In fact, because of the indeterminism, there will be a huge overhead in terms of resources. Believed to be insufficient for quantum computation, linear optics, and so one needs nonlinear. So passive devices using linear optics are not scalable. So we need more work has to be done. Recently, we have also used the chip in another application, which is called autoencoder. And what autoencoder does is that it scales down. So you have a set of data, which is a low dimensional data in a high dimensional space. You would like to find out where this plane lies. And so typically, in a nutshell, it is you have a space, a density matrix in a higher dimensional space. You can always find the eigenvectors and eigenvalues. The ones with high weights, high eigenvalues in your density matrix, you keep. The one with low, you throw. And so this is called an autoencoder. So basically, you compress the space. And with that sort of ideas, we showed that you can do noise reduction. And I'll not go into the details, but certainly. And we have also shown that you can take a three-dimensional qubit, reduce it to 2, and with 2 dimensions, you can do perfect teleportation over long distances, and then you decode using the reverse of the autoencoder. And you can get much better fidelity to some extent. So these were the fidelity that's obtained. So I can't pronounce this. Hopefully some of you can. Thank you. Thank you very much.
Thanks, Kwek. Anyone has any questions? Kwek. Yeah.
I might have gone a little bit too fast, but
sorry?
yeah, it's
is there
just
something-
more of an overview of the whole thing.
Hello, Professor Kwek. Thank you
Yes,
for
yes, yes.
nice
Thank
talk.
you. Yeah.
This is Tanmoy. I have one question regarding the laser writer based waveguide fabrication part. So what I understand, you need femtosecond laser for writing the structures, right?
Yes, yes.
Yeah, but so in case of silicon, so this works in silica, it is fine. So if we want to do it, let's say in silicon or silicon nitride, this does not work, I believe.
That's right. That's right.
Yeah. So in that case, this polarization problem, does it still there in case of silicon or so, or you use phase shifter, this kind of thing? What is
so for us, we do it lithographically, and so it's on the plane. So we do it layer by layer, lithographically. We don't use polarization degree of freedom because we couldn't tilt our beam splitter, and we just use path encoding. So it's like dual rail in some sense, and you can still achieve most of the performance that you get from polarization degree of freedom. Now, the photon is something very interesting because it has many, many degrees of freedom. So you can now actually use a combination of them. So that's how we overcome it.
Okay, thank you.
Moreover, we can do it with silicon nitride.
Okay.
Silicon nitride has the advantage that it has some nonlinearity. So we are hoping that the next generation, in the next 10 years or so, we are able to produce silicon chips with better nonlinearity, hopefully with eco-friendly materials, and then we become a force to be reckoned with, right? Because entanglement becomes easier.
Right. So silicon nitride, what I understand, you can use it for source also, right? If you use
that's right.
photo mixing,
Yes.
so that's also an advantage.
Yes,
in
yes,
terms of kind
yes,
of
that's right.
integrating it on the chip.
Yes, yes. You can actually integrate it into with pillars.
Right.
Yeah, on pillars to get single photon source. And nowadays, this is preferred photon source.
Right. Right. Okay. Thank you. Thank you very
Thank
much.
you. Thank you for the question. Right. Any other question? This is the year for the quantum science and technology, as it was mentioned earlier on. And hopefully, you might want to ask more questions.
There are
about
two
quantum science.
questions.
Yes.
Yeah, there are two questions from YouTube Live.
Uh-huh.
The first question is it possible to design the photonic chip into the parameterized quantum circuits that we know nowadays? This is the first.
The parametrized quantum circuit uses entangling gates. The direct translation of parametrized quantum circuit is not possible at the moment with a silicon chip. Simply because we use linear optics, there's no non-linearity. And with no non-linearity, you cannot have an entangling gate. However, like I said earlier on, we are looking for nonlinear materials. And then at that stage, then we can do PQC, parametrized quantum circuits. I hope that answers part of the question.
Thank you. And another question is that with different QC architectures, how do qubit from different QC system communicate with each other?
So quantum, one of the things that we've been looking at in recent years has been how to let superconducting qubits talk with photonic chip and therefore with other devices like ion trap. Basically what we're looking at is hybrid quantum computation. So there are certain things that the photonic chip can do much better than the superconducting qubit. And there are certain things that the superconducting qubits perform way, way better than the photonic chip. So the whole idea is to harness what the superconducting qubit can do and what the photonic chip can do. So that is one direction we are now slowly looking into that.
Thank you, Professor.
Okay, so I have a question. So you are not using polarization degree of freedom, right? For
No,
of this
no, I don't. Yeah, because we use lithographic chips.
So which degree of freedom is actually being used?
Puff. Essentially, it's more.
Okay.
Yeah.
So
You
and
can-
also you were mentioning you have done QKD, over long. So it means you have some fiber optic cable to which these photonic chips are connected to.
With
And that-
QKD, you can, because you don't have the circuits are not very complicating, you can
Mhm.
even exploit polarization degree of freedom.
Okay, so but then the chips are connected with some fiber optic cable where this.
Sure. But the connection with your optical fiber circuits are typically for CVQKD, continuous variable, and not the discrete variable. With
Okay.
discrete variable, you have to connect to dark fibers, right? Basically, it must be a fiber that is dedicated to QKD.
So how long is usually this fiber? I mean.
We have shown that it's possible with in the lab, 50 kilometers is very short distance. We just coil it into this huge pillar.
Okay.
But in real experiment, you just do it over the laid out optical set, and you can do that. Yeah, you can test it. I have a colleague at NUS who is been testing a lot on mainly on dark fiber because it's on discrete variables, but he certainly is keen to go into continuous variable if it's marketable. Yeah, that's Alex Link for your information.
Okay, thank you.
Yeah.
So, Kwek,
Yeah.
are you also like looking at space-based experiments with respect to what you're looking at?
Space at the moment we are still well, Singapore is not the best place to do space. The cloud cover is very bad. But in recent year, of course, we have tried to improve certain aspects,
Hmm.
communicating over longer distance because that's the advantage.
Right.
But what is interesting is that with the chip,
Hmm.
I've not tested out yet, but I'll be willing to test it out with the MDI QKD. So if you have three or rather two satellites
Hmm.
and they need to establish a common key,
Hmm.
it is very interesting if the common key can be established through MDI QKD.
Hmm.
So you just install the chip onto the two space station, which is not a lot of space. You can do that with CubeSat, and then they communicate all the time with a ground station. The ground station, of course, is not secure. It's just your Alice, and no, your Charlie, and so it can broadcast information. By collecting the broadcast information, then the two satellites can now get entangled. And I think this is an interesting scheme in some sense, if it can be done.
Okay. Okay. Yeah. So, do we have any other questions from the audience, either here or online?
You might want to ask questions like,
There
why
is
is 2025 the International Year of Quantum Science and Technology?
Uh,
There is one question from YouTube.
Uh-huh.
So the same from the same audience. This question is: can we, for instance, perform entanglement swapping with superconducting qubits to photonic qubits?
Ah, uh, it's difficult at the moment. Let me see. It's a good question, actually. So you're talking about two photonic qubits being entangled, and then you have two superconducting qubits that are entangled, and now you want the photonic to be entangled to. I think that can be done already with microwave. With superconducting qubits, they can already swap with the because superconducting qubits talk through microwave, right, with the waveguide as well. So there's a lot of photonics present in the superconducting qubits. So uh, uh, I think typically one of the photons is entangled to the microwave, and then via the microwave, you can then get the two distance superconducting qubits entangled through this entanglement swapping process. So if you are thinking in terms of microwave, then sure, that's been done. But what is more interesting is, can you then do it with real visible light, for example? And then that question amounts to a frequency conversion. The frequency conversion can be tricky. And this is something we are looking into, actually, because it is sometimes good to transfer information that are in the superconducting qubits completely into a photonic platform. So that I think has not been done. Not even entanglement swapping. I don't think it's been done. It's not so easy, basically. Simply because of the frequency conversion. And they're not very efficient at the moment.
Okay, so I have one more question. I mean, so you mentioned about Madame C.S. Wu experiment.
Uh-huh.
Did she really connect her observations with quantum entanglement? I mean, does she
No,
mention?
at that time, quantum entanglement was still not in vogue.
Right.
She knew about correlation though,
Hmm.
because 1949, Bell has not published his result, and 1949 she knew about the Verstrangen from ideas from Schrödinger. So she knew something about entanglement, but
Did she? Does her results require presence of entanglement?
yes. It requires. In fact, it was used efficiently.
Okay.
Yes.
Thank
So in fact, we all realized that C.S. Wu was the first person, in fact, to start this whole entanglement business experimentally. Just like she did it with parity.
Okay.
So there's in fact a recent article in Physics Today that highlight her importance in research.
Okay.
It's remarkable because she's a lady, and she's a lady in the early 40s, right?
Yeah.
1940s.
Yeah.
It's
Yeah,
difficult times.
yeah, but after 10 years, she did win Nobel Prize, right? So,
She didn't get the Nobel Prize. She was not, she was not nominated. And
Oh, okay, she was nominated. Yes, she didn't get it. It
she
was
was not even
Leong
nominated. Yeah.
Yang who got it.
Yeah.
Okay, okay. So, any more questions?
One question from the YouTube audience. So the
Yeah.
question is that, as you mentioned that one cannot generate entanglement without using nonlinearity, but KLM protocol says conditional photon detection with linear optics can generate entanglement.
Yes.
Can you please comment on that? Yeah.
Yes, with linear optics, we can generate entanglement, but probabilistically. So if you want to have 100% of a chance, one way is to, let's say you can only succeed with 1/10 of 10 parts in one. Then what you can do in order to generate certainty is to have 10 of these devices. So in other words, you are going to trade this non-indeterminism with adding more resources. And what the KLM says is that you need an exponential number of resources eventually. So that was the main lesson we learned from that paper. Does that answer the question?
Yes, I hope so. Yeah.
Yeah.
Thank you, Prof.
Thank you for the question. It's important to think deeper into that actually.
Are there any more questions? Yeah, okay, on Zoom. Okay, it is already asked. Okay, are there any more questions?
As of now, there is no question from YouTube live.
Okay. So I think we can give also Anek Dhanyawad to Professor Kwek for his this
Thank
very
you. Thank you for
beautiful
the
educative talk.
invitation.
So
Very
thank you.
happy to give a talk. It's not time for dinner time in Singapore.
Thanks,
Bye-bye.
Kwek. Yeah, bye.
Yeah, thanks, Shipas. It does. All this I
Thank you.
can share. Yeah.